Okay, so let's try this really crazy question that seems to be in the next section, and I don't know why it's here. So this is number 23 out of 16.4, which says we are trying to find the volume of a solid orange wedge. I don't know whether they mean orange the color or orange the fruit, but it doesn't matter because that information is definitely crucial. And they say that my solid orange wedge, I'm going to envision that as color, just so we're all playing on the same place.
Is it a solid wedge that's orange, or is it a solid orange that is
No, it's a solid wedge that is the color orange.
Oh, okay.
If you assume that it's an orange, then you can assume both.
Well,
Fair point.
If it's the fruit, is it truly solid? Because that's...
Okay, point is, it's orange, okay? And it's bounded by x is bigger than 0, y is 0. So let's see, it's in the right-hand side, yeah?
Yeah.
It's bounded by y is 0.
So it can't go below it.
Okay, so maybe I should start drawing.
Yep.
Okay, so x, y, z. So x is bigger than 0, so I'm on the right-hand side. The y's live between 0 and, ooh, what are these guys?
Planar bounds.
Yeah, those are planes, right? You guys with me on that? So y is 0 is the which plane?
The XZ.
Yeah, that's the xz plane. And then y is x over the square root of 3. That's normally like a line, right? That feels like a line, but the z is unbounded. Yeah, so it sweeps up and down. So I should draw that though, right? So what's the slope on the line y is x over 3? Yeah, so that's... Is that not what I'm going to say? I hope that's... So... y is 1 over root 3x, right? Yes?
It's not the line, right? Root 3x.
Yeah, so you go over root 3 in the x, and you go up 1 in y. So, square root of 3 and 1. I'm not going to draw the left half because
X cannot go past that.
I already forgot that side existed anyway. You guys cool with this? And the other one is here.
Get all the
And then I
ones.
need to sweep those up and down, right? That's the y is 0, and this one's y is 1 over the square root of 3x. Okay, and then there's a sphere of radius 5.
Oh, geez.
Okay, cool. So a sphere of radius 5 looks like you go up 5, you go out 5, you go out 5, you go out 5. You guys see that? And I'm going to play a little connect the dots game here, and it's probably not going to go super well. So I need to go like that, and like this, and then like that, and that one needed to be dotted. Yeah. Except for the fact that that got a little bit too straight. I think I'm okay with this. And then what else?
It goes down the Z's.
Yeah, you guys see this? They didn't restrict the Z's, right? That looks like half an orange slice. Oh shit, he's the wrong marker. That's half a black slice, right? But I needed an orange slice, not half a black one. So you need to go. Yeah, so this picture needs to be flipped over on the z-axis, right? So you need the same thing for minus z's. So you should get this. And that should be a circle, right? And then there should be a connecting. You guys see my orange slice here?
Yeah. No,
Okay.
I only see a black slice.
Yeah. Damn it. I really needed an orange marker to pull this joke off. Okay.
Oh, there's one right there.
Oh, good call. There's an orange marker right here. I'm not going to do that. I already missed the boat on that joke. Mark, can you make a note on my? Can you make a note somewhere to tell me to write on my syllabus to bring an orange marker this day? Okay, so how do I even set this thing up? I'm supposed to find a volume, right? Okay, so to find a volume, what do you do?
X squared plus y squared plus c squared, right? Would be the base function.
Oh yeah, so what's the base function?
X squared plus y squared plus c squared is 5? Or 25?
That's just
Yeah.
the.
So what function are you trying to find the area underneath here?
It wouldn't be underneath anything really. It would just be inside, right? Inside this line.
Yeah, so there's a couple different ways to set this up. One of them would be to triple integrate over this thing, which I'm going to call S for, I'm going to call OS for orange slice, right? So you could triple integrate 1 d volume over the orange slice. That's what they're asking you to do here. Why 1? Good question. Because 1's the density of volume. So what I'm adding up here, right? That's going to be the height that I'm kind of multiplying by the area of a base. In this case, the area of a base is a, like you might think to yourself, this is a dx, dy, dz, right? So that's a little x, a little y, and a little z. And then I need to multiply by the height of a function in there. But I don't have a function whose height I want to evaluate. I just want to add up all the volume.
So 1's just your default then?
Yeah, so 1's just the default. Like if you want to find the length of an interval, right? And this is the dumbest way to find the length of an interval. You could integrate from a to b 1 dx. Right, that'll give you b minus a. You guys with me on that? If you want to find the area of a region, you could do the double integral of 1 over the area. And then the first thing you're going to do, right, is you're going to make some bounds, and you're going to integrate, and you're going to get an area under a curve. We could do that same thing here by saying, okay, I'm going to exploit symmetry a little bit. And I'm going to say that this is twice the double integral under what curve? Yeah, I need that sphere, right? So I'm going to go from 0 to the square root of 5 squared minus x squared minus y squared.
We don't care.
If you don't want to exploit symmetry, you can just go.
Or the other one would be the
Yeah.
one negative of that, right?
Oh, wait. I screwed something up. What did I screw up? You guys see what I just screwed up?
You want X is n.
That's not a bound.
That's a function.
That's the function I want to be integrating.
Say, like they were stuck with either an X or a Y, depending on how we do it.
You guys see that? So that's me thinking about my orange slice as these are the heights, right? Times a little area in here. And then my area in there is over this kind of like off triangle thing. Right, it's like a little sector. You guys all see that? So you could get away with that. That would also be an option. You guys want to set that one up first, just for kicks?
Sure.
It's not too bad, actually. I need a, what am I integrating with respect to there?
Dx and Y.
Yeah, that'd be a dx dy, right? And we'd have to figure out what the bounds are. Guys cool? Does that make sense? Okay, so let's do that. Let's figure it out. This is not the question they asked, though, right?
You
You
cut
know,
that
they
in.
want us for us to, number one, evaluate it in spherical coordinates, then evaluate it in cylindrical coordinates in two different ways. And then to calculate the volume without integration.
So they want me to not evaluate, but just set it up.
Okay.
Fine. Oh yeah, they just want me to answer which coordinates are most efficient. I don't know spherical and cylindrical yet, so let me set this up in polar and we'll get there. Okay? So in polar, I'm going to use this guy. So I'm going to exploit symmetry a little bit. I'm going to do double the integral over this little sector of this thing. It's cool. But that little sector sucks in XY land, right? Okay, so let me draw the little sector. Looks like this. This is 5 long, right?
Like,
And this slope is the square root of 3 and 1.
I think we're supposed to be doing the other slice, like from y to that slope, not from x.
No, I'm supposed to go from y is 0.
Okay,
Y is 0 is that xz plane.
okay.
Up to the y is 1 over the square root of 3.
So we,
No,
oh,
that
y is
happens
0 is an
to be-
x plane, duh.
Yeah, y is 0 is an x thing. Well, really it's an xz thing, right?
Yeah.
Okay, so I got, this is my region that I'm trying to integrate over. Right, the inside of this. Is all with me? Okay, but I want to convert that thing to polar. So let me see. There's a 2. There's some integrals. That thing is the square root of, convert to polar, right?
R squared.
5 squared minus r squared.
Good. That is 5 squared minus r squared. Guys with me? Okay. And then what else do I need here? Good. You need your conversion factor, right? R dr d theta. It's all good with that? That's my dx dy turned into the r dr d theta. And this other thing was my function I'm integrating. Okay. Bounce? Where do the r's live? Picture? 0 to 5? Yeah, seems like, right? Like, that thing's a circle, right? Okay, so the radius goes from nothing up to 5. Cool. Good. Where do the angles live?
Well,
See y equals.
which angle are we talking about?
Yeah.
Angle on the Z.
Good.
Or X,
So it
Y?
starts at 0. I don't.
So I'm talking about these angles, right? So the way I get in here, right, is I have r's that go from like 0 out to the edge, and then I have thetas that sweep through here. So if you sweep this orange thing, how much angle do you need to cover the whole region that I'm talking about?
Inverse tangent of 1 over root 3.
Yeah. it's just-
Wait, where does that go? That's one number. I need 2 numbers, right?
0 to inverse tangent of 1 over root 3.
Perfect. So 0 is your first angle, right? And then the other one here is arctangent of 1 over the square root of 3?
Why is it 1 over root 3? If the function
Because y equals
Opposite over adjacent.
Opposite over adjacent. Yeah, there's a like the function thing going on, right? And then there's just a trig thing, which is you want to find out this angle. And that angle makes a triangle that's got an opposite side of 1 and an adjacent side of square root of 3. So what's the arctangent of 1 over the square root of 3?
Give me a second.
Oh, come on, guys.
5 over
Don't
6.
do that. Which one is it?
Oh my gosh, it's a 30, 60, 90.
It's a 30, 60, 90 triangle. And this one is the 30. That's a pi over 6. Yes? Remember that triangle. It'll come back to haunt you.
How do we get that 5 or 6? The 3? Oh, okay.
That's an equilateral triangle, right? So all the angles are the same. And the sum of the angles in a triangle is pi. So they're all pi over 3, but you cut that one in half to make the triangle we're talking about. So that's a pi over 3 cut in half is a pi over 6. Cool? Good? You guys figure this out? Is this easy integration or hard integration?
Or I mean, like,
It's obnoxious.
yeah.
Is this obnoxious or
Yeah.
you're saying obnoxious?
You have
But
to do like
I've seen
I tried
worse.
parts.
oh God, no,
No.
I've seen worse.
no, don't do parts. Yeah, this is easy U sub. You got this.
Oh, you saw.
Always think of U sub. That should be your first go-to trick. If it's not if it's not a function that you recognize as the derivative of something, U sub is your next best bet. After U sub, in Calc 3, abandon, go convert to a different coordinate system.
Okay.
Right? Because in Calc 3, you get this tool that's actually easier than trying another integration technique.
So it's
Cool? So if you can switch to another coordinate system, try it for a second. If not, then you do like integration by parts or trig substitution or some garbage. Right? But if it's not easy U sub, try switching coordinate systems, and then hopefully things will be easier. Cool?
You think the same thing?
Okay. You guys can do this. I'm going to leave that. Now I'm going to answer the question the book asked, which is, can you tell me about spherical coordinates here? Yeah, so you guys don't know about spherical coordinates yet, right?
Oh, yeah.
So spherical coordinates should be like polar. Polar does circles really well, right?
Yep.
Is this a chunk of a sphere? Yes. Is it a chunk of a cylinder? No. Which one's going to work better, spherical or cylindrical? Spherical. Right? Like that's the dumbest way to think about this, like just a words match. But it's actually the right way to think. This is a piece of a sphere. Spherical is going to be easy because spherical does spheres. It's not a piece of a cylinder, right? Cylindrical does cylinders really easily. Cool?
But cylindrical, all you have to do is add on the z, so wouldn't that necessarily be easier for this problem?
Yeah, it wouldn't be a lot harder than what we just did.
But you still want to use
So I think you guys can get cylindrical right away because
Yeah, it's just-
um,
You use another sort of theta function. I'm assuming because the z, it's from negative pi over 2 to pi over 2.
okay, so let's set this thing up in cylindrical. You guys can trust me on this. I'm just going to throw the conversion factor in here. It's r dr d theta dz. And we're going to integrate 1 because it's asking a volume question, right? Okay, now, where do the r's range from? Wait, I need to change the order. What's the thing I'm going to get rid of first? Like if I think about this, right? Sweeping r's is this way.
I thought this was-
Sorry, that's thetas. Sweeping thetas is this way. Sweeping r's is this way. And sweeping z's is like this, right?
Let's get rid of that first.
Okay, which of those is the most obnoxious? The z's, I think, are the worst because they start at the bottom of the sphere.
Wait.
So they start from down here and go up, right? So they have bounds that depend on the other variables. You guys see that? Like that's function to function stuff. So you got to get that out of there first. So your z's, where do your z's start?
or no, sorry, from pi over 2 to pi over, negative pi over 2.
From negative square root of
The z is bounded by the function.
Yes.
Because you can still do it that way, but then you would have nasty r's and thetas. You want to have a constant r and a constant theta.
You guys see this? Right, the z's start at something that depends on where you are in here. Right, like if I put that point that I'm talking about if I put that over here, my z heights are different, right? You guys see that? So it depends on where you are, that z value.
So
You guys see that?
xy plus y squared, or x squared, y squared, z squared equals 25 and solve for x then?
Good, yeah. So you can think about this as x squared plus y squared plus z squared is 25, right? And actually, it's probably better to think about x squared plus y squared as r squared, right? That'll make my life a little easier. Otherwise, I'd be doing Cartesian, right? You could do Cartesian here, it would just really suck. Okay, so this would give me z squared is 25 minus r squared. So that'd give me z is plus or minus the square root of 25 minus r squared. You guys all see that? Okay, so your z's range from minus the square root of 25 minus r squared to the square root of 25 minus r squared. Wow. You guys with me? Okay. Then where do your r's range? R's range from 0 to 5 still. This is where that thing I was telling you about smashing comes in handy, right? You guys see that? Because you've got this horrible thing. Once you take the z's out, smush, tip, then you're looking at this thing again, right? So you got, where are your thetas range? 0 to pi over 6 again, right? Please note, if you do this, right, your first integration is going to be dz. You're integrating r dz. You're going to get rz. Then you're going to evaluate from this thing to that thing. Sorry, from this thing to that thing. And you're going to get 2 of that times an r. You guys see that? You end up doing the friggin' polar integral all over again. Right?
So we turned the function and the double into another.
Yeah, I exploited symmetry a little bit. And here I was thinking about it as a function. I was finding the volume underneath. And here I was thinking about it as the bounds on the integral. You guys see that? Okay. Let me briefly explain you how spherical works, just so that we'll be able to get the coordinates for this easily, or the bounds for this easily. So for spherical, we're going to do the triple integral, 1. And then here there will be a conversion factor that I haven't told you yet, so I'm going to put a dv there. Okay, we have to go get that conversion factor out of somewhere. We'll go get it in a minute. You guys all good with that?
Okay.
So there's going to be, that's going to be dv. And there's going to be some missing stuff, and then there will be a d rho, d theta, and a d phi here. Which will be the spherical thing, right? And there will be some kind of like, this will be like an r, but it's not. So we'll figure that out in a minute. How about our bounds? So the rows are just the radii, but they're now spherical radii, so they aren't limited to the xy plane. So where do the radii go here? Like, if you go out in any direction, is it always the same?
Yeah.
It's always the same, right? Because it's a sphere of radius 5 that's making the outside shell here. So the radii go from 0 to 5. Right? Where do the thetas go? 0 to pi over 6 still. That theta is still the same. Okay, now, and this is the part that's hard. You have to remember where the phi comes from.
So would this be 0 to pi over 2?
So the phi is this angle here.
So it should be negative pi over
That
2
sweeps
pi over
down.
2.
So it's the angle off of the positive z-axis.
Oh, off the
From
pi.
Zero to pi.
From what to the z-axis?
Zero. Yeah, pi.
From what to the
Like
z-axis?
it pans off the z-axis, what's the stop on?
Is it 0 at the z-axis?
Good question.
Positive. So
Would that be like 180 degrees then?
Yeah, that seems reasonable, right? Because why would you need the other side? Because you can, so if you think about this, right? Like, I want to reach any point in three-dimensional space. Oh shit, I need something to stand on. Okay. I want to reach any point in three-dimensional space, right? So let's assume, oh god, I'm going to hit this. Okay, don't let me hit that. Mark, you're in charge. Okay, that's positive z-axis. We'll assume the x-axis is that way and the y-axis is this way. You guys all good with this? Okay, so if I want to reach any point at all, I have a radius, right? That's this thing,
Okay.
right? So I've got stabbing as a motion. That's that radius. And then I've got a theta, which is
Side strike.
this rotation, right? So far I've got this, stabbing, and rotating. And that's off of the positive x-axis, right? You guys with me?
Yep.
So I need a way to get to, well, off of this plane, right? So I need some kind of elevation.
Some sort of overhand strike.
Yeah, that. Mark! I told you were in charge, then you let me hit it. Okay, so that thing is going to be that declination off of the z, right? And then Rayler rightly asks, how far down does it go? Where does it stop?
Well,
Stop on
sounds-
the z-axis on the bottom.
Yeah, because if I want to get to something like back here, right? That seems like it could take a overhand and back, right? But alternatively, I could do so I'm starting here, right? Kind of thinking 0, 0, 0. And I need an out, right? So I go out the appropriate distance. And then I need to go, I've got a theta, right? So I'll go around, and then I'll use my declination to get down there. So that thing really does vary from 0 to, I almost hit it again, from 0 to pi. And you don't need the other stuff. You guys see that?
Okay.
Based on position, would it actually be like pi over 2 to 3/2?
So on this guy, keep in mind it's angled off the vertical. So that starts at 0 being vertical,
Okay.
and then comes down through. Do I need all of it here?
Yes.
Yeah, here you need all of it. If you just wanted the top half, so if you wanted to exploit symmetry, I'm going to put a 0 to pi there. But if you wanted to exploit symmetry, you could do 0 to pi over 2 and then double it. And that would give you just the top half and then doubled.
Well, what's the point of that?
You guys all good with this?
Yeah, 0.
Cool? Questions, things? This integration, right, probably be pretty easy because this is like a rectangle, right? You guys with me on that?
Mm-hmm.
In spherical, spheres are like rectangles. The conversion factor is the thing that's going to give you a little bit of a headache, right? Because there's variables in there, so you'll actually have to do some integrating. You guys see that? But you'll probably get good at integrating the integration factor, right? Because you're going to integrate that thing a lot. Cool? Questions, Steele?
Other than what is the conversion factor?
Perfect. Cool. Let's go find the conversion factor. So let me shut this off and we'll go find it.